Good morning, everyone. My name is Andy Fan. I'm an assistant professor of manufacturing engineering of Oregon State University. We're in the school of MIME together with Joe. And together with our collaborator, my colleagues, Dr. Braxender and Dr. Carl, we had this opportunity to work with OMIC on this project. And my former student, Eddie Lee and Xianzhe Hu, they are a contributor as a student. So a little bit about my background. I got my PhD from University of Massachusetts, and my research interest is in the sensor design. So we design sensors and design new sensor modalities to improve the visibility of the manufacturing process. And also I am interested in applying the sensors in different processes to monitor the process and make use of those information to estimate, for instance, the health status of the machinery and also the quality of the product. And for this project, we are looking at the tool wear on the cutting tool. So when we use the cutting tool to cut the metal during, for instance, turning process, there will be tool wear developed on the cutting edge. And the tool wear can be developed through different reasons, and they show different forms like flank, crater, build-up, and chipping during the cutting process. So when the tool wear is very small, they are fine for the cutting process. They don't have a very significant effect on the surface of the part. But when the tool wear becomes large, when they're going beyond a certain threshold, they will have a significant effect on the surface. Sometimes there will be burn marks due to the over high temperature during cutting. And sometimes they will make the cutting process very unstable. And you will observe the increased surface roughness, for instance, and also sometimes inaccurate geometric dimensions. So for that reasons, we need to change those cutting tool or cutting inserts periodically. So practically, those cutting inserts are mounted on a piece of metal called cutting shank, tool shank. And this cutting insert is replaced at a certain time. But some of the cutting inserts could be very expensive, so replacing them too early would result in economic inefficiency. Okay, but if we replace them too late, the worn-out tool could also produce failure parts. As I said, increased surface roughness and even inaccurate geometric dimensions. So for that reason, we are thinking of the idea of building a smart tool. So we are going to embed sensors inside these cutting tools and make use of the sensor data information to estimate the current status of the tool wear and provide a heads-up warning to the manufacturer. Okay, right now it is a good time to replace this cutting tool, and otherwise it will worn out in the next cutting pass. So that is the basic idea of this project. And we are facing quite a few technical challenges for this approach. And here I'm listing 3 of them. So in this chart, I'm showing the approximate or general cutting tool wear development process. So the horizontal axis is representing the cutting length. So the cutting, how many cutting passes or how many meters or inches has been cut by that cutting tool. And the horizontal axis, vertical axis is the tool wear size. So we measure the size of the tool and the tool wear. And if you look at their relationship, they are quite nonlinear. Okay, so this kind of nonlinearity makes this process or tool wear process hard to be predicted. So in its initial state, you can see a flat region. In this region, the tool wear develops very slowly, and we can produce good parts with the tool at this time, at this period. But at a certain threshold time, this tool wear will increase very fast. So that is accelerated stage. And during that stage, the tool wear will develop very fast. And when it's going through across the threshold, it will fail. So the first challenge for us is to understand which kind of sensor or which kind of sensor data and even which features in the sensor data is most correlated with the tool wear. There are many of them hidden in the raw data, and we need to figure them out. And the second is how to predict the tool wear based on the sensor data. So that would require to establish a mathematical model and make use of the model, train the model and make use of the model to do the predictions. And the third challenge, major one, is how to evaluate our work, experimentally and theoretically. So, toward that purpose, we developed this kind of methodology. And the methodology is based on the physical observation of the cutting process. So, when the tool wear developed on a cutting tool, okay, everybody can understand that the increased friction will produce additional heat and additional temperature increase on the cutting edge. So, increased temperature is one of the phenomena we are looking at. And also, the instability of cutting process induced by the tool wear will produce additional vibration and additional noise during the cutting. And also, the tool wear would increase the cutting force. Not very close example, but everybody might have feel that, is when you are doing some kitchen work, you use a knife to cut the meat or some hard material. If the knife is wearing out, you can feel that the cutting force is higher. So I'm doing some of the kitchen work, but ordered by my wife. And so in that case, if we have sensors embedded in the cutting tool and measure them at very short distance from the cutting edge, we can, and if we can detect all of those variations, okay, we can make use of those information to measure and predict the tool wear on the cutting edges. So that is the basic methodology we have thought about. And in a word, we want to develop a sensor-embedded smart cutting tool and being capable of predicting the tool wear based on the sensor data and in situ through the model-based machine learning. And our technical approaches are based on two assumptions. Okay, these assumptions are very important for establishing the mathematical model, but we believe they are also physically, realistic. So the first assumption is that we can digitize the cutting process into a couple of states, from the very beginning when the tool is brand new to the state that the tool is totally wear out. Okay, and in each of the states, for instance, we can represent a state by a single cutting path. For instance, 1 foot of cutting. And those cutting states, within each of the cutting states, the tool wear status is stable, but the change will happen from one state to another. Okay, so that is the first assumption. Very simple. And the second assumption is that the future status of the tool wear is determined by two factors. The first factor is the previous state of the cutting tool. So when we are doing the next path of cutting, if the previous cutting state, in the previous cut or previous path, the cutting tool has already shown some tool wear, it will be different from the case when the cutting tool was brand new in the previous state. So that is the first piece of this assumption. And the second is factor determining the present state is the sensor data. So vibration, cutting temperature, force, noise, and so on. So these two combinations will co-determine the present or the future state, and we can make use of them to predict the status of the toolware in the future. So those are the second assumption. Okay, to predict the future status of the toolware, actually we need to build two models to represent the two relationships. First one is from the sensor data to the future states of the toolware, and the second one is from the last state of toolware to the future state of the toolware. So those are two models. And practically, we adopted artificial neural network to represent the first relationship, and unscented Kalman filter to represent the second relationship. So actually, there are more candidate algorithms or models for us to choose to represent those conditions or relationships. For instance, if we have a large amount of data, we can also replace this artificial neural network with convolutional neural network. So that is one of the approach we are doing with the second phase of the project. And also, the unscented Kalman filter can be replaced with the other filters to represent the state and the state relationship. We specifically chose these two algorithms for this project, specifically for based on the condition and constraints of the present approach. Okay, so with these two, our idea is to make use of the data, collect the data during the graduate stage, okay, stable cutting stage. We collect the data at this time, and at this time we also sample the ground truth of the toolware, okay, and make use of those information to train our model. And after this stage, okay, graduate stage or initial stage, we no longer need to measure the ground truth. And solely based on the sensor data to measure and predict the toolware in the secondary stage of the cutting process. So we learn the process, or learn the relationship in the first stage, and predict in the second stage. That is the basic idea of prediction for our project. And technically, we have a few milestones for this project, including the design and the prototype of the smart tool, built the algorithm mathematically, and validate the system, and did a lot of experimental tests to collect the data and train the model. Okay, and in the next section, I'm going to talk about the major outcomes of this work. So our project just started from the summer of 2022 and ends at the summer of 2023. So at the very initial stage, we have designed the first version of the smart tool with only one sensor, the thermocouple, right underneath the cutting edge to measure the cutting temperature. And then in the next month, we further revised this design and add a sleeve over there to the cutting shank and include more sensors over there. And then at the end of 2022, we come to the final, not final, but semi-final design with multiple sensors embedded. And you can see the thermocouple is embedded right beneath the cutting edge. And strain gauges measuring the cutting forces. And acoustic emission sensor measuring the noise, and accelerometer, which is measuring the vibration generated during the cutting process. And finally, in the spring of 2023, we come to the final design, and you can see everything is consistent with over here, but we have some revision from the electronics and mechanical design of the smart tool. So the final design includes the same amount of sensors as we've shown over here. And so this is a test snapshot after we developed a prototype of the smart tool. And on the left, this is the cutting process, and the right side, these are all the sensor data we sampled from the sensors. And you can see the acceleration or vibration in X, Y, and Z orthogonal orientations sampled by the vibration sensor, and the acoustic emission, the noise over here, and the temperature, cutting temperature, and also the strain or cutting force in orthogonal orientations. And during the process, you can hear the high-pitched noise. And actually, this video was taken when this cutting tool is almost brand new. Okay, so the noise is still very mild at this time. But you can see the increase of the temperature during the cutting process. It increases when we increase the cutting length. And also there are some variations in the cutting force and in the noise as well. So to measure the ground truth of the tool wear, we also developed a system based on a micrometer to observe the tool wear from inside the machine. So before doing this, we also tried the case to install the cutting tool from the machine and place it underneath the microscope to take a clearer picture, because the light, background light will be very consistent in that case. However, we found that when we install tools, there will be some inconsistency developed due to the tolerance of the assembly. So finally, we come to this idea to measure everything within the machine. But it's also give us some challenge, and we're going to show them in the next few pages. And in this case, we take a picture of the tool and focus on the tool tip, cutting edge, and measure the width of the tool wear. So with this microscope based on the images. So this chart is showing the measured ground truth as a function of the number of cutting passes or cutting length. And you can see that with the increase of the cutting length, the tool wear width increases by following an S-curve. And this kind of trend is approximately matches with our general understanding of the tool wear development. And those blue dots are the real data, raw data we measured by using the microscope. And you can see that they varies a lot during this process. And one of the reasons we assume is that when we put the microscope inside the machine, because the tool wear orientation of the surface could vary when it's developed. So every time the image of the tool wear could be a little bit inconsistent. And also there could be chips developed on the cutting edge during the cutting process and making this ground truth measurement unstable. But if we fit them with a curve, we can still see that trend in the ground truth measurement results. About the raw data from the sensors, so this is a glance of the vibration data we got from the accelerometer. And specifically, we tried the principal component analysis for this raw data, and specifically picked up the frequency component. So this is the result for fast Fourier transform, and we picked up the component at 3 kilohertz. And this frequency is actually associated with the spindle speed of the cutting process. So if we adopted different cutting conditions, we can also determine the most related component or feature by making use of the similar relationship. And if we extract the height or the power of this frequency component, we can also produce the trend of this power of vibration along the cutting passes. And we can see that this trend is similar to what we saw on the ground truth, but a little bit different in the trend, in the angle. Okay, so it's developed a little bit slower than what we saw on the ground truth. And another kind of data we are looking at was the temperature data. So for temperature, we observed from the previous video that the temperature keep increasing during the cutting process. So for each of the cutting paths, actually, we were trying to take the secondary section of the temperature data when the temperature becomes comparatively stable in that stage. So that is this, about 60 seconds. And we take the average temperature from this section and produce those temperatures in each of the passes along the cutting, overall cutting path. And we can see that the trend is almost a straight line, but a little bit flattened when it's getting close to the end of the life, of the lifetime. Okay, so based on the sensor data and the ground truth, we specifically built this artificial neural network model and unscented Kalman filter model to make the predictions, to correlate the sensor data and previous state to the future state of the two-wear. And specifically, actually, as you know, as an academia institute, we need to develop something new so that the students can write a paper and publish it. And for this kind of work, actually, we also added temperature as a factor that determines the state transition in this unscented Kalman filter. So this is a novelty we have added to this model development. And we are going to show the difference between the new model and the conventional unscented Kalman filter model with respect to the performance of this prediction. And by using, based on these two models, we are using the first 160 cuts. Okay, the data sampled in those cuts, make use of them to train these models to learn about the relationship between the sensor data and the two-wear. And then we stop measuring the ground truth, okay, virtually. Actually, we measure the ground truth over there, but no longer use it with the model, and solely based on the sensor data to make predictions in a secondary stage over here for predicting the two-wear width. And here is the result. So the first one I'm introducing over here is the result by using the conventional unscented Kalman filter plus artificial neural network. And we can see that the blue curve is the ground truth, and the red curve is the predicted results. And we will focus on this section because over here, this is the prediction without any ground truth measured. And we can compare that, and we can see that this conventional Kalman filter, or conventional model, can somehow predict the trend of the two-wear development, but not that accurate. It can show some increase over there, but the difference is large. So with our revised unscented Kalman filter, by adding the cutting temperature into the stage transition function, we can much better increase the accuracy. And we specifically measure calculated the error over there. It is within 5%. So during the prediction stage. So that shows the efficiency of our model when predicting the two-wear during the cutting process. And so this is the major results we have gotten from this project. And so as a conclusion, we have developed the hardware of the smart tool, and we have also developed the software, the algorithm to make predictions based on the sensor data and based on the previous state of the two-wear. And the experimental data has validated our model, and we have got an average prediction error of about 5%. And based on this result, we also produced a journal paper. And if you are interested in the details of our algorithm, you can also refer to this publication. So presently, we're working on the secondary phase of this project. So from the previous introduction, you can see that we need a certain amount of data in the first stage of the cutting process to learn about the relationship between the sensor data and the toolware. So in the secondary phase, we are aiming at reducing the learning period and reducing the amount of data used for training. And even we want to collect the data from one of the cutting tools and make use of it, make use of the trained model to predict the toolware on the other cutting tools. So that is the target, the goal of the present approach. And we have some methodologies over there. And one of the major advancement of this work is that we are going to include the strain gauge measured data, namely the cutting force, into this scope to make a consistent correlation between the strain or cutting force and the toolware status. Okay, that's my presentation, and I'll be happy to answer your questions.